We're going to start this lecture by proving a result about uniqueness of two-sided inverses. So specifically what we're going to prove is the claim that's written at the top there, which says that if you have a function f from x to y which has two inverses, g and h, then actually g is equal to h. So that's what it means when people say two-sided inverses are unique. They mean that if a function f has two inverses, so two-sided inverses, g and h, then actually g must be equal to h. And the way we'll prove this is just by copying, literally word for word, an argument we made at the end of the previous lecture when we were showing that a function was a bijection if and only if it had a two-sided inverse. So here in this situation we have a function f from x to y, and we have g and h, which are two-sided inverses of f, and we're just going to consider g and do the same trick as before. So g is the same as g composed with the identity on y, because we know composing with the identity doesn't do anything. But the identity on y is equal to f composed with h, because h is an inverse of f, a two-sided inverse of f. So in particular, it's a right inverse to f. Okay, we're now going to use associativity. So let's just record why this was. So this is true because h is a right inverse to f. Okay, next, by associativity, I can rewrite this as g composed with f composed with h. And we'll do the exact same thing as before. Now g is a left inverse to f because g is a two-sided inverse to f. So this is really just the identity on x composed with h. And finally, I've just got h again. So tracing through these equalities, g is equal to h, which was what we were supposed to prove, so we finished our proof. So that means we can make the following definition. We define if f is invertible. So this is more of a piece of notation than a definition. If f is invertible, we write f with a superscript -1 like that for the inverse of f. And the reason this notation now makes sense is that, having proved this claim, we know that an invertible function only has one inverse, and therefore it makes sense to have a special piece of notation referring to that inverse. Okay, let's now move on and talk about shoes and socks. So the first thing, well, one of the things you do in the morning when you wake up is that you put your shoes on, you put your socks on, and then you put your shoes on. And then later on in the day, you want to reverse this procedure to get your feet back to where they started. And you do that. Well, you don't take your socks off, then your shoes off, because feet don't work like that. You have to take your shoes off first, and then your socks off. So let's think of this in terms of function composition. The function that you apply to yourself first thing in the morning is, first you do the socks function, and then you do the shoes function. Right, remember that g composed with f is the function which has, as a rule, do f and then do g. So I have to write it in this order to mean the function you get by doing socks first and then shoes, which is the correct way round. And as we said just now, the way we invert this procedure in the evening is we first do the inverse shoes procedure and then we do the inverse socks procedure. So this is socks inverse composed with shoes inverse, right? The way round matters, the order matters. So inspired by this, we are now going to prove a theorem about invertible functions. So our theorem is if f from x to y and g from y to z are invertible, then the composite function g composed with f is invertible too. And in fact we can say what its inverse is. G composed with f inverse is f inverse composed with g inverse. And the important thing is the order, right? When you take the inverse of g composed with f, you get the inverse of f composed with the inverse of g. You've swapped the order, just like we had to swap the order of socks and shoes. Okay, so the proof is easy. Once you know the answer, once you know what the inverse is, you can then just check that it really is an inverse. So in order to prove this function, in order to prove this theorem, I have to show that the composition of g and f is invertible. And to do that, I just show that this thing which I claim is an inverse really is a two-sided inverse. So we just check that f inverse composed with g inverse is a left and a right inverse to g composed with f. So I'm just going to check one of them. I will check that it's left inverse. So this is going to be our check on the left. F inverse composed with G inverse composed with G composed with F. Well, I can use associativity to rebracket this however I like. So I choose to rebracket it like this. Remember, associativity doesn't just apply to compositions of three functions. It allows you to rebracket a composition of arbitrary length however you like. Now in the middle there you've got G inverse composed with G, which is the identity. So this is the identity on Y composed with F inverse. And again, composing with the identity doesn't do anything, so this is F composed with F inverse, and that is the identity on X. What have I done? I've got these the wrong way around, haven't I? So these, I should have had an inverse there and no inverse there. That's more like it. Okay, that's better. So this shows that F inverse composed with G inverse is a left inverse to G composed with F. And similarly, you can show that it's a right inverse. So I'm not going to do that, but you can check that. If you like, you just need to make the exact same argument flipped over. Okay, that completes our proof then. Let's now make two observations. So first observation is that you can generalize this. This is about the composition of two invertible functions, and it says that the composition of two invertible functions is again invertible, and you get its inverse by composing the inverses of the two functions in the opposite order. But that works more generally. So more generally, if f1, f2, and so on up to fn are invertible, and if you can compose them, so if f1 composed with f2, composed with f3 up to fn makes sense, then it's invertible. And you get the inverse by composing Fn inverse with Fn minus 1 inverse, and so on. So let's write this carefully. F1 composed up to Fn inverse is equal to Fn to the minus 1 composed with Fn minus 1 to the minus 1 down to F1 to the minus 1. Okay, so that's our first observation, that if you want to take the inverse of a composition of an arbitrary number of functions, you do that by composing their inverses in the opposite order. And observation number 2 is that we can rephrase this theorem in terms of bijections, or actually something related to this theorem in terms of bijections. In our last lecture, you'll remember that we showed that a function was a bijection if and only if it was invertible. So if and only if it had a two-sided inverse. So in the theorem that we wrote up here, we showed that if you compose two invertible functions, then the result is also invertible. So we could have, I'm going to call this a corollary. My corollary is just saying that we can now replace the word invertible with the word bijection to get that the composition of two bijections is also a bijection. Okay,